Stop it and start it again because there's a short video I want to show you at the beginning of NMR, and for I guess reasons, copyright reasons, I can't show video or they'll block the video. All right, so KPC. We're going to go over partition coefficients. I'm going to tell you what it is you need to know. We're going to solve some questions, and then, like I said, it's going to be your decision on whether this is something you want to study for the test or not. But I am telling you there is a non-zero chance it can show up on a paper 5, so I'm going to give you some paper 5 practices as well when we get closer to the time, so you can see what those look like. All right, KPC, partition coefficient. This is defined, and so one of the standards is just to define it. It's the ratio of the concentrations of solutes in two different. And I saw in the notes, like I looked through the old exams, and they didn't have the word immiscible there, like as a required word. But I think that that's an important word, so I'm going to describe what that is. This was in the textbook. In two immiscible solvents in contact with each other. So immiscible is something, for some reason, I do not see this vocabulary ever in the Cambridge curriculum until right here. Anybody know? Maybe if you took bio, what is immiscible? What is immiscible? What does that mean? So it means that these two liquids don't mix, like oil and water. So all immiscible means is not mixable. So miscible means that your two solutions do mix in with each other. That word miscible. Two liquids that are soluble in each other. So an immiscible solvent means that you've got two different liquids that will form two different layers. So that means you've got what we would call a heterogeneous mixture. My best way to think of it is like oil and water. You know, oil and water don't mix. They clearly make two different layers. And so this says that we can find something called the KPC, which is the partition coefficient, by seeing how much of a solute dissolves in each of these layers. And that's dependent on its solubility, its polarity, versus each of the solvents that it's in. And so that's what it says here, because this is the final standard about chromatography. When I have a mixture and I have my separation that I got last class in chromatography, right? And we know that we can separate into different components based on polarities. This is based on the relative solubility in two different materials. The mobile phase and the stationary phase. And so the more something gets stuck in the stationary phase, the less it moves. The more it's soluble in the mobile phase, the more it moves, is the idea. It has to do with the relative polarities, the extents of the polarity of whatever it is I'm trying to separate versus what my solvents are. And so the greater the solubility, the greater rate of movement in the mobile phase. This is actually a device that you would use in an organic chemistry class. They're expensive, so no, we don't have it. I think I have one in a cabinet, but I have to, like, it's got like plastic wrap and everything around it. I haven't, used it yet. But this is a type of device, and this is actually the same little stopcock that you would see in a burette, like when you do the little lever to turn a burette. And this little device right here, it allows for one liquid to pour out and then the other. And so here you see two different colors. And so this would be solvent 1. And this down here would be solvent 2. So whatever the two solvents are. And then these two arrows right here represent equilibrium. So how much of your solute is dissolved in here versus how much of your solute is dissolved in here is the idea. And so you can use that. Basically, you can shake this together and then take a part out and then figure out how much is dissolved in each layer is the idea. And so I'm going to give you an too easy question, like it's not like a Cambridge question on the next slide, but I found it in an old workbook just to give you an idea of how you could analyze these types of questions, and then we'll get a look into what this actually looks like on paper 4. So KPC turns out to be this. It's a ratio between my solute in two different solvents, where A stands for solvent A, and B stands for the concentration of it in solvent B. One of the things to be aware of is KPC is unitless. What do I mean by that? the units always
That's
cancel because it's just a concentration divided by another concentration. So it's always going to be unitless. And so let's take a look just using this equilibrium. And we're going to say that this is solvent A. And you'll see why in the other questions why I have to tell you this. And this is solvent B. If there are 4.5 molarity of NH3 dissolved in the organic layer and 2.3 molarity of NH3 dissolved in the aqueous layer, calculate the KPC. And even before we move on, what do we mean by organic layer and aqueous layer? Like that, because that's actually said a lot by organic chemists, like that terminology. What does that even mean? Why would those separate? Why would that be separated into two layers, an organic layer and an aqueous layer? Axel, I saw your hand up though. You sure? Okay, Isa?
Because aqueous water, polar.
Aqueous, water, polar is the way brains should like translate that. When they say aqueous layer, they're saying, okay, this is how much dissolved in the polar. And then what do they mean then by organic layer? Like what is the intention of saying it like that? Isa?
Organic CC, non-polar.
It's going to be more non-polar. We don't know how non-polar because we don't exactly know what the organic substance is that we're using, but it's not water. It's not as polar as water. Water's super polar. So it's going to be more non-polar. And so that allows you to have that separation because remember, like dissolves like. Polar things dissolve into polar things. Non-polar dissolves into non-polar. So what they're trying to say here, if I had that funnel like this, is that one of these layers is polar and one of these layers is non-polar, and they separate just like oil and water because oil is non-polar and water is polar. So it's that kind of idea that's going on. Okay, so that's the concept. That's the idea. And whatever solute I have is going to dissolve some in each layer. And they're asking us to figure out, well, what is that sum in each layer? Here they're saying, well, what's the KPC? So here's how we do it. So KPC, this brackets right here means molarity, if I'm given it. So I want the molarity of my solvent A. What's my molarity of my solvent A? Do I have it in the questions? What is that number? It's this, right? Because that's the organic layer. So it's 4.5, right? So it's 4.5. And that's molybdenum minus 3. And on the bottom is my concentration of solvent B. What's my solvent B? I labeled it as aqueous. So it would be 2.3 in the aqueous layer. 2.3. These cancel, and then you just divide the two numbers. And you do 4.5 divided by 2.3, which, like I said, is overly easy. Don't worry, it'll not be as easy when we get to the Cambridge questions. And so the answer that I get from this is 1.96 or 2.0. Check my math. I think that that's what I got. 2.0. Yes.
Is the organic layer always the top layer?
That's a good question. And typically, yes, it's because of density. Density would give you the top and bottom layer. So oil is on top of water because oil is less dense. So that has to do with the density of the materials. Okay, so what does this actually mean? A KPC of 2.0? Like that means that 2 times the amount of NH3 is dissolving in the organic layer than is dissolving in the aqueous layer. Does that make sense? So this means, you may want to write that down, that 2 times the amount of NH3 dissolves in the organic layer than the aqueous. Or a ratio of 2 to 1, right? Because this is just simply KPC at its basics is a ratio of how much your solute dissolves in one layer versus how much it dissolves in the other layer. And if you understand that, you'll understand the math that follows a little bit better. I'm sighing because of this. Looking at the next question. Okay, so this is about, like I said, I don't think they give you a question this easy on the Cambridge exam. It will look more like the follow-up 3 practice questions that I have. But the concept here is what I wanted to teach, like what's going on, so you get a general idea. Yes, Andrea.
Who else wants to pick up?
Aqueous, then the aqueous. And then this is just saying 2 to 1, because that's what it means, 2/1. Okay, so this is what an actual question looks like. I'll get you up on your paper 4 and paper 5. Let's read it through, because lots of reading. And then I want to point your attention to how many marks this is worth. And then we're going to go ahead and do it out of the 100-mark test. All right, so it says, ammonia is soluble in both water and organic solvents. They have different polarities. That's why it'll be separated. So again, it's ammonia they're talking about. We have an aqueous solution of ammonia shaken with immiscible, that word again, not mixable organic solvent, trichloromethane. If you want to, you can like sketch that out just to know, hey, what is that? Was trichloromethane? I did. Like, that's CHCl3, right? That's trichloromethane. The mixture is left to reach equilibrium. Samples are taken from each layer, the top layer and the bottom layer, right? So you've got your little they call this a separatory funnel. And you've got your 2 layers, sample taken from this layer, sample taken from this layer. They take out those samples and they run a titration with dilute hydrochloric acid. So samples are taken from each layer and titrated. And then they give you the following information. A 25 centimeters cubed sample from the trichloromethane layer requires 13 centimeters cubed of a 0.1 molarity HCl to reach the end point. And then a 10 centimeter cubed sample from the aqueous layer requires 12.5 centimeters cubed of a 0.1 molarity HCl to reach the end point. Calculate the partition coefficient of ammonia between trichloromethane and water. Anybody have a suggestion of where we can begin? Why did they give us the titration stuff? Ramon.
We can find the moles of each substance first.
Of which substance?
Of ATL for both layers.
For the layers. Okay, yeah, you can go that way. Issa, did you have something around what you said? Okay. So they're getting at something here. What is NH3 by definition? And let me clarify, let me ask a more direct question. Is NH3 an acid or a base? NH3 is a base. I'm gonna write that on the side. So the reason why they're titrating the ammonia they take out, like the samples they take out of each layer, is to figure out by reacting ammonia with acid, how much ammonia is there. And they're saying that, oh, this is the amount of acid I needed to get like the end point, which means that's how much ammonia that I'm going to have. So how would I do that? Like, how can I go about that? How can I figure out the ammonia from this information, Issa?
First, you only need to write the equation.
The chemical reaction. You could do that. You can say, okay, so then it's going to be NH3 plus HCl goes to NH4Cl. That's what that would, like those two would react that way. Something important to note here, this is a 1-to-1 ratio. Like it's a monobasic base. Those are big words, but it's a base that only is 1, and then the acid is also 1 as well. There is a shortcut formula that you can actually use for this that I'm going to bring up. And I think I did bring this up to you in the past when we were looking over paper 5. There's a shortcut formula if you don't want to go through the whole solution stoichiometry. What do I mean by that? You mentioned, oh, well, let's find the moles of the HCl. Why would we do that? Because we go from moles of HCl to moles of NH3, and then we go from moles of NH3 to concentration of NH3. That's 3 steps, right? And that's 3 steps twice and that's actually not even the whole thing. We still have more to do after that. Remember how many marks this is worth? Worth 2 whole marks. There is a shortcut formula you can use, and Cambridge uses it in their mark scheme, actually. So it's a Cambridge approved shortcut. And it is almost the same exact formula as dilution. Do you remember that?
Like M1 or something else.
M1 V1 equals M2 V2. This formula actually works as is if you have a 1-to-1 ratio. You can actually use this formula with your two concentrations and your one volume, or your two volumes and your one concentration, to solve for the other one that you're looking for, and not do 3 steps, but do this whole thing in 1 step with one formula. But what if it wasn't 1-to-1? This formula actually wouldn't work if this wasn't 1-to-1. I think, go over something. Go ahead, Isa.
We just, and once we find that idea, just multiply that on both sides.
You would, and they put in this little extra factor to account for that, the same idea that you're saying. If not 1-to-1, like it's not a 1 acid and a 1 base, you would use this. You're like, what is that? I think I mentioned it before, but this would be the amount of H plus in your acid. And this would be the amount of OH minus that's being released by your base. So that's an alteration to the formula. We actually don't need that for this question. But on paper 5, you could need that, specifically paper 5. So we're going to use the shortcut formula because I'm not taking the time to do all 3 steps, and I don't have the space here to do all 3 steps twice. And that doesn't even get us to where we need to go. Like, that just gets us this information. Okay, so I'm going to do this first bullet point. It says a 25 centimeters cube sample from the trichloromethane layer requires 13 centimeters cubed of a 0.1 molarity HCl. Doesn't matter which side is the acid side and which side is the base side for the M1V1 formula. You pick one side for acid and one side for base. So I'm going to say that this is my base side and this is my acid side. So I'm going to look for M1. So I'm going to do M1 times 25 equals 0.1 times 13. Why didn't I change my volumes from centimeters cubed? They automatically cancel. Because like all the units cancel properly here, so I don't have to change my units. And in the mark scheme, they won't. So I get 0.1 times 13, which is
0.3.
1.3. And then divide by 25. And I get 0.052. And what is that actually telling me? What is 0.052? What is that saying?
Concentration.
That's the concentration of NH3 in the trichloromethane layer. Following me so far? Okay. But for KPC, we need the concentration in both layers, right? So now what do we got to do? We got to do the second bullet point. So again, so this was the first. That was 1. I'm going to mark this 2. Do it again. So M1V1 equals M2V2. This time, I'm still looking for M1 times 10 equals 0.1 times 12.5. Divide both sides by 10. And I get M1 equals, see if you get the same thing as me, I get 0.125. And that would be the concentration of NH3 in this layer. At this point, I've earned 1 mark. If you did all of this correct and you got 0.052 and 0.125, that's where they award the first mark here. So then, what do I do next? I have to find KPC. So for the KPC, what's the formula? And this is a little tricky. How do you know what goes on top and what goes on the bottom? They have to tell you. So the wording here tells you the ratio that they're looking for. They said between trichloromethane and water. So what that means is they want the molarity in trichloromethane on the top and the molarity in water on the bottom. So they're telling you what ratio they want. So this is gonna be the NH3 in the CHCl3 on the top, and then the NH3 in the water on the bottom. Does that make sense? So they said between the trichloromethane and the water. So one on top, the next one on the bottom, that they say. That's the ratio. So let's just plug in the numbers. So 0.052 divided by 0.125. And your final answer here, if you do this right, is 0.41. And that's it. Now, I read in this specific mark scheme that they had accepted, I'm thinking they don't normally do this, but in this specific mark scheme, they had accepted if you had flipped those numbers accidentally, and you did instead of 0.052 over 0.125, you did 0.125 over 0.052, but I'm telling you that this is the way it's supposed to be. And I don't know that all mark schemes would accept that. All right, ready to move forward? Let's try another. KPC of benzoic acid. So this time they're giving you KPC. They're telling you the partition coefficient of benzoic acid between octanol and water is the number 79.4. And they give you a solution of 0.4 grams of benzoic acid in 25 centimeters cubed octanol, and they shake it with 125 centimeters cubed of water. Calculate the amount of benzoic acid extracted into the water layer. And so this question to me is the hardest type of question. Let's see if you can follow along. What are they saying is going on? We took this, we put it in octanol, right? We took benzoic acid, we put it in octanol, and then what did we do? We shook it with water. And so what's happening is some of the benzoic acid transfers from the octanol, I'll get it shortly, from the octanol layer to the water layer. But how much? We do know the partition coefficient is 79.4. And what that means is that 79.4, yes. Was this 4?
Yeah.
Okay, no problem.
Thank you.
We know that the partition coefficient is 79.4, which relates the concentrations between how much is dissolved in octanol and how much is dissolved in water. So see if you can follow along with me to how this works. The first thing I wanted to say, and I made a little note here, is to remember that KPC is unitless. I mentioned this, I'm saying it again for a reason right now. As long as the units match. So as long as the units match, you can cancel it. Which means, in this question, you do not have to use mole over dm cubed. Instead, you can use gram over dm cubed, because g over dm cubed over g over dm cubed, it would all cancel. And so that's going to make your math a little bit easier. You can try to work it out with mole over dm cubed and tell me if you get the same answer, but the math does end up being more complicated than as it's presented. So here's what we're going to do. First, KPC, that formula. It's the ratio between the solubility in two solvents. Here it's the solubility in octanol versus the solubility in water. So it's the solubility of benzoic acid in octanol over benzoic acid solubility in water. That's because, and it's that because they told us. That's the order. Between benzoic octanol and water is 79.4. So here's where the math is. KPC is 79.4. We have that. How much grams of benzoic acid do we have in octanol? It's not 0.4. Why is it not 0.4? How many grams of benzoic acid do we have in octanol when it's shaken with water?
guess.
Remember, we took 0.4 grams, just to give you the terrible drawing. This is the device. We took 0.4 grams, right? And that's in 25 centimeters cubed of octanol. But then we had 125 centimeters cubed of water. And some of that 0.4 went into here, right? So how much benzoic acid? I say Ramon's hand.
We have what's it called? 4/5. I kind of see where it's going. Like where
Once I say it, hopefully it makes sense. But I'm trying to see if I can extract it out of you first. Yes.
2x, no, 0.4 minus x.
Yes. That's right. So it's 0.4 minus x is the amount of grams I have in the octanol. Why? Because a non-discriminate amount, an x amount, went from here to there, right? We don't know how much that is. That's actually x. We have to solve for that. We have to figure out what that is. So 0.4 minus x is the grams. What's the volume? Because remember, this has to be a concentration. So concentration is at its basic an amount over a volume. So what would the volume be of octanol? I wrote 25. So I'm doing mine in grams over cm cubed. That's how I'm doing my units. I'm doing grams over cm cubed over grams over cm cubed. And all my units are going to cancel like that. So that's my one layer. That's my top layer, grams over cm cubed. But now I got to do that again for the bottom layer. So how much grams of benzoic acid are going into the water? X. We don't know. That's how much transferred, right? So X would be going in the water. And how much water is there? 125. Doing it this way eliminates as much unit conversions as possible, knowing that all the units cancel. So it saves you some time and pain. But this is still painful. Why? What is the math here? What do you have here? You have a division over a division. Isn't that a division of fractions? So how would we solve this? Lisa?
Just flip the one at the bottom.
Yes, so flip the one at the bottom is the best way to go. So 0.4 minus x over 25 multiplied by, change it into a multiplication of fractions. And so now you're going to take this and flip it. And so now it becomes 125 over x. That's your formula. Solve for x. How do we solve this for x? There's so many ways you can go about it, but I would start by multiplying by x on both sides to get it out of the denominator. Like personally, I would get x out of the denominator first always. So I multiplied both sides by x. So I get 79.4 x equals, what do we have right now if I get rid of the x? Some of you may recognize, hey, could I do 125 divided by 25 right now? Do I really have to distribute the 125? No, I could just recognize that this number is 5, right? So this is 5 times 0.4 minus x. Distribute the 5. And hopefully I wrote that down. Let's see. I got 79.4x equals 2 minus 5x. I move 5x to the other side. I get 84.4x equals 2. Divide by 84.4 on both sides. And I got 0.0237 equals x. What does that represent? What does that mean? What does x represent? How many grams went into the water layer? Isn't that what this is asking for? Because it's how much was extracted, how much came out. This is the answer, 0.0237. 2 marks. What? Marks. Continue. All right, that was our second. I told you we'd do 3 because I'll only do one, especially on a topic like this. If I'm going to cover it, I'm going to cover it enough so that you get enough different types of practice questions to see the full spectrum of what you could be asked here. Okay. Notice how I didn't use molarity. I changed it to grams over cm cubed. As long as the units cancel, you can do that. That's why I wrote this note first. You can use any, thing over volume, mass over volume, or moles over volume, as long as they cancel. Now, like I said, you could practice with trying to switch it into molarity. I think I've tried that before, and I just end up getting confused. So this is the easier way to go.
That works.
All right, last practice question on this, and then we can move out of this topic into the other major topic. Because like I said, this is a few marks. The other topic is one that's almost guaranteed to be a ton of marks. That we're going to start today and continue next class. All right, so practice question. State what is meant by the partition coefficient KPC. This is literally defining. I'm just going to write what it is, or the minimum of what you have to say to earn the mark. It's the ratio of concentrations of solutes. And they just said in 2 solvents. I put immiscible, but they said in 2 solvents. So in 2, I would write immiscible. Why am I writing parentheses around it? It was not required in the mark scheme, but I think that it should be there. So I'm putting it because it's important that the solvents are not soluble in each other. And I think in other mark schemes, they probably would have put that. So I'm putting it there. All right, and here's our last question. So this one should be very similar to the last one. Look at how much space they give you. The partition coefficient for a compound X between carbon disulfide. Is carbon disulfide polar or non-polar, by the way? Isn't that non-polar? That's so non-polar. Non-polar and water. Polar is 10.5. And what does that number 10.5 mean? Like, if I'm reading a KPC, what does that mean ratio-wise? It means 10.5 to 1. But what does that mean? 10.5, the amount, is dissolving in carbon disulfide, then it's dissolving in water. Which means that whatever my solute is probably more non-polar. Does that kind of make sense? Whatever it is, I don't know what it is, but it's probably very non-polar because it's mostly dissolving in the non-polar thing. Okay, so just throwing that out there, just so you know these numbers, they do have meaning attached to them. I've got 1.85 grams of this whatever X is. It's dissolved in water. We put it in a volumetric flask of 100 centimeters cubed. Then we take out 40 of that, and shake that 40 with 25 of CS2 and leave that to equilibrium. Calculate the mass of X, extract it into the CS2 layer. And I thought this one was a little bit tricky, but definitely within the scope of what you could be asked. KBC formula, what is that? It's the ratio of the 2 solvents, right? So it's the concentration of X in, what is the first one this time? What is the one on the top this time? CS2. The CS2 has to be on the top. And then on the bottom is the water. Am I going to want to use molarity here, or am I going to want to use gram over centimeter cubed for this question? Like for ease of math. Gram over cm cubed. Because they cancel. Gram over cm cubed over gram over cm cubed cancels. So here we're going to want to use gram over cm cubed for our concentration units, which, by the way, is the same units of density. Okay, so let's think about the situation. 1.585 grams of X is dissolved in water, and we put it in a volumetric flask of 100 centimeters cubed. So think about what's happening here. What is a volumetric flask? Because like paper 5 exists, you do have to know your equipment. What's a volumetric flask?
Wow.
It's this one. Do you remember that one? And it has one job, and you go to that line, and you make that line, you hit that line, you're good. You don't hit that line, you start over. Do you remember that? That's the volume. That's the volumetric flask. So you made the solution in a volumetric flask of 100 centimeters cubed. But you didn't use 100 centimeters cubed of it, right? You took out 40 to do the reaction. That's important. And so this is the prepared solution. Has 1.85 grams in this, but you took out 40 centimeters cubed for the reaction. Where you should get into the two layers. Okay, so now we've got the situation. Let's take a look at the CS2. What is the piece of equipment? It's called a separatory funnel. They will not, I don't think, ask you to memorize this one, but it looks like this. And you've got this, and we know that we've got 40 centimeters cubed in here. And how much was the other one, the CS2? How many centimeters cubed is that? 25, right? And then this is water. And so you basically shake these two things together and they separate, is the idea. We started with how much in the water? How many grams do we have in the water? That's the trap. It's not 1.85. Why isn't it 1.85? 1.85 was dissolved in 100. Shaken. Dissolved. 40 of that was taken out. How many grams is dissolved in 40 centimeters cubed if you stirred it very well? Like if you dissolved, Ramon, I see your hand up.
0.74 grams.
0.74 is correct. How'd you get it?
Because I just multiplied 1.85 by 0.4.
times 0.4, or 40 over 100, right?
Yeah.
You could do 40 over 100 because it was 100 centimeters cubed, but you took out 40. So then it's 0.74 grams in 40 centimeters cubed. There's 0.74 grams originally here, right? There's 0.74 grams originally here. But isn't some of that then transferred to the CS2? So now, question is, we had 0.74 grams in here. This is transferring into the CS2. How much is transferring into the CS2? It's the same question as last time. Isa.
For the, why can't we use the
1.84?
I was using MB equals MB, that formula, then I realized that it's because I don't know.
You don't have the information for that. There's no titration here. Good?
Mhm.
Do you understand why it's 0.74 and not 1.8? Because it's 40 instead of 100. Like you took the 1.8, put it in 100, but then you took 40 out. So it's only 40% of what you had is what you're actually using for the reaction. And so it's 0.74 grams. But that's not how much is in that layer because some is coming out to the CS2. How much is coming out to the CS2? Isn't that X? So for our actual math, the CS2 is on top. How many grams of X will be in CS2? We don't know that. So that we're going to call the X. What's the volume of CS2? It's 25. Do we agree? Are we good with that? What about the bottom? The water part. How many grams of this is in the water? Is it 0.74? Didn't some come out into there, Ramon?
What's that for minus X?
0.74 minus X. Because it's 0.74 minus how much came out to the other layer. And then the bottom number would be the volume of the water. The volume of the water in here is 40. Give me a picture to draw to give you understanding for this like teamwork question. Okay, so that's the math. We still need the number for KPC. What was the number?
Wait, miss.
Yes.
I have a question. Why does the, x over 25 shouldn't that go at the bottom? Because it's a y.
No. The terminology tells you what goes on the top and what goes on the bottom. The KPC, look at the first sentence again. For compound X between carbon disulfide, that means CS2 is 10.5 and water is 10.5. The ratio says CS2 is on the top and water's on the bottom because that's the number they gave us. If you want to flip it, you can, but it ain't going to be 10.5. It's going to be 1 over 10.5. Like, to do the math right, you could flip the ratio, but then that number changes. You see what I'm saying? Because it's a ratio between the two. All right, so then this is equal to 10.5. Like, all of this is equal to KPC, which is, for here, 10.5. That's the number. So our math is 10.5 equals, what can I do with these two fractions? It's double fractions, so you got to flip the bottom one, right? So it's x over 25 times 40 over 0.74 minus x. The rest of your ability to get this correct is your ability to do algebra because you're solving for x, right? And so we're going to do that. Multiply by 0.74 minus x on each side. What's 40 over 25?
No.
I get 1.6. And then it's math. Yes.
So since you're like flipping the fractions anyway, the grams line up to be able to cross multiply and so then to be able to cross out
For what? What would
that with a fraction for half. You can cross out the x and instead of 40 and the 25, you just divide it by 12.
you can divide 40 and 25 each by 5 and then
Yeah, and then
simplify the fraction.
but then why would you get an x's?
You can't get rid of the x's because it's being subtracted. It's not being multiplied. They're different. Like in rational equations, any x that's being added or subtracted cannot be canceled. I'll repeat that. Any x that's being added or subtracted cannot be canceled. So because that's a subtraction, you can't cancel that back. That is the actual mathematical reason why that can't happen. It won't work. Okay, so then we do the rest of the math here. I get 7.77 minus 10.5x. This will
Are we supposed to get a
1.6x.
negative number?
What?
Is it possible to get a negative number?
Nope. Plus 10.5x plus 10.5x. I get 1.77 equals 12.1x. It means something went wrong in the algebra. That's what that means. And then the answer is 7.77. I just can't write 7 well. And then this is 0.642. That's it.
That's negative.
Because we were looking for x. So is that worth the 2 marks?
No.
It's your decision, right?
And you said like there's a chance that
There's a chance it can be on paper 5.
that it could
like-
be like half a paper 5.
And then it would be half of paper 5. And then they would just ask a bunch of different questions about it. That's why I said we got to know the process regardless.
Okay.
So I would study for paper 5, but not necessarily for paper 4 unless you're going for like a super high score on paper 4. Because it's only worth 2 marks on a paper 4 and it takes time too. All right, so we are done with separation techniques finally. Did I remember last class when I told you I didn't think I could cover that in 7 minutes? Do you now understand why? I got a little bit too ambitious. Because it was like 9:07 and I was like, I don't think I got the time for that. Like I could have, I guess, speed ran it, but the time it takes to understand it is like significantly longer than the 8 minutes that I had to get to the donuts. That's why we stopped a little early. All right, so now we're going back in time to AS Chem. And I think I mentioned last class that this unit is technically 3 sections that are kind of just 3 different things you have to learn. The first part of this unit was polymers, right? We talked about addition polymerization and condensation polymerization, and then how that fed into stuff like amino acids. Then the second part of this unit was separation techniques. That's chromatography. That's electrophoresis. And then that wrapped up with the partition coefficients. Like those are all separatory techniques, how we separate mixtures. And then finally, the last part of this unit is how do we look at a graph and analyze what molecule that we have. This is something that Cambridge has been steadily moving from A-level chemistry to AS chemistry. It used to be content that was only in A-level chemistry, But as you may remember, we did have a lesson last year where we went over IR and where we went over mass spec. So we are now going to review IR for the next segment of the class. And depending on how much time we have, I'm going to introduce you to NMR, which is our major technique that's new this year. And it's a big one. It's important. It's what real, actual practicing scientists use all the time. And so the nice thing about Cambridge is you get a view onto what, real scientists do. All right, so IR spec. You may or may not remember this from last year. I'm going to give you a crash course review. You would see graphs like this, and you'd have to read the dips and the curves, which they call peaks for some reason, but to me, they look more like troughs, like bottoms, but they do label them, they call them peaks, and you look for the bottom of the peak to tell you what you have. And so you look anywhere where you got some major stuff going on around the 1300 range and greater. And so here, because I see this wide peak around 3200, I know automatically that's alcohol. You're like, was I supposed to remember that? No, because you have a table that's coming on the next slide or very soon that has them that you would have provided to you on the test. But a practicing chemist would actually just know them by heart because he seems to walk. So it's like, oh yeah, that's an alcohol for sure, 100%. Just because of where you see the patient. And if I saw something around 1700, I'm like, yeah, that's got a C double bond O in it. Some kind of ester or, ketone or aldehyde. And so that is what we mean by IR spectrum is we use IR. So we use IR to determine functional group. That's all it tells us. So by that, I mean, it can tell us how it's possibly going to react because we know the functional group, but it doesn't tell us how many carbons, what type of isomer it is. Is it a primary, secondary, tertiary alcohol? It only tells us alcohol. And so what you're going to see is all of these different techniques you're going to learn work in tandem. You use the IR to give you the functional group. You use the mass spec to give you the molar mass and like little pieces. And then you're going to use NMR to find exactly how many hydrogens are on each carbon and how many carbons you have. It's called the carbon NMR. So you'll find out the exact molecule, its whole entire structure after we're done with the next couple lessons. So IR spec only tells us functional group, not how many carbons, not how many hydrogens, and so you would need to employ other techniques. We will employ those techniques over these next few class periods. So you will find out by, stretch goal is by the end of next class, but if not by the end of next class, then the one after, you'll get to analyze complete molecules. So this is also something you would do in organic chemistry too in a university. So anybody who is taking a STEM major that is going to need to have a major where they take the whole sequence of chemistry courses would be utilizing these techniques as well. So by taking this class, you have a leg up because you'll already be aware. And I actually, because my mind is very analytical, I love this topic. I remember my professor saying that it was like the hardest topic ever. And I remember doing it, I was like, oh, no, what are you talking about? But that's because everybody has their own personal preferences, likes, and dislikes. For me, the hardest part of organic was not this. It was memorizing a whole bunch of random reactions because that doesn't jive with my brain as well. But this is analytical in nature. So if you're very analytical, hopefully you'll do quite well here. So this would be provided to you if you have an IR question on the A-level test. And is it possible, even though IR is not in the standards, that they could give you an IR question on paper 4? Yes, that's why we're recovering it. And we'll recover all the techniques because there's a non-zero chance. You could be given all of the different techniques and use that to come up with what molecule you have. These are the absorption ranges for the different functional groups. And really what's being sensed is the vibration of the bond. The vibration of the chemical bond shows up at different numbers. And so if I have a C single bond O, which is present in alcohols, ethers, and esters, you get something, what I think is a trough, but they call a peak, between 1040 and 1300. And S means that it's strong. Strong means goes down far. Weak means only maybe halfway. And then you've got C double bond C alkenes, 1500 to 1680. C double bond O, that's your like carbonyl groups typically. C triple bond C, alkynes, we don't really talk about those, but non-zero chance. CH, alkanes, this should always be there. So I usually don't look too much at this area when I'm looking at a graph because you should always have a peak around 2900 and that just tells you you have CHs. If you've got an organic molecule, guess what? you've probably got CHs because like that's the whole thing about most organic molecules. So I don't look for this typically, but if I had an arene, which is a benzene, I see something between 3,000 and 3,100 possibly. Amines are in a very similar area to alcohols, but you know that you have a nitrogen instead of an oxygen somehow. And then carboxylic acids are very broad between 2,500 and 3,000. And that's important to know. Yes. Every other. It's so this is an old data booklet, so I'm not even sure that they even talk about this anymore, but it's when you have that pi bonding delocalized system. So every other group is got a pi bond. That's what it conjugated means. Yes. You can scan through and go. And so on the next few slides are some practice questions. These are very similar to the ones that we did in AS, just to kind of jog your memory on what we used to do here close to a year ago. So here's the first checkup. This comes from the textbook. I probably should have like updated my image, but I was too tired, sorry. So it says, look at the two infrared spectra below. It says, which one of the infrared spectra is butanol and which one is butanol? Go ahead, Issa. Yes. And it's just like that. Between 3,200 and 3,500, I see a very wide peak there. That tells me that that's got to be an alcohol. That has to be an alcohol. And that's not here between 3,200 and 3,500. So that one's not an alcohol. This one, on the other hand, A has a sharp peak in the 1,700 range and a sharp peak in the 1,700 range because it says it here is something that has a C double bond O. And so that's going to be the distinguishing characteristic here. A is the ketone and B is butanol. Explanation. How we explain that? So it says explain your reasoning. A has a sharp peak around, what is that, 1710? Around 1710. CM minus. Whereas, go ahead. D has a sharp peak around 3,300. And you can estimate. So this is just telling, hey, what's the difference in the functional group here? On the next couple slides, I think I put some paper 1 questions. I know that that's AS Chem, but like I said, we need to go back and review. So we're going to take a look at a couple questions. I think we did do these or something very similar to these last year, but I think it's important to review them just to make sure we kind of jog our memory. This one, they gave us compound P. What could P be? So remember, you get to look at this chart to help you out, to figure it out. When I'm looking, I look at certain areas. I look at the 1,700 area, personally. I look at the 1,700 area, and I see if there's a peak there. No peak means no C double bond O. So no C double bond O going on around here, which means it cannot be that. It cannot be that. It cannot be that. So what does it have to be? Propanol. Man, I wish that was a people 1 question. Gas. Okay. This is the Next Gen Roundtable Miami Youth Summit, March 12th. Is that Amy or Sarah? I don't know. Ashley and Denny. Daniela. Do you know what this is?
It's
What is it actually? What does that mean? What time does that start? What time are you leaving? 7:30?
going the whole day.
Uh-huh. Okay, let's continue. Substance T was analyzed and found to contain 62.07% carbon, 10.34% hydrogen, and 27.59% oxygen. What is it? So once again, I would look for two areas, 1700 and 3200. Do I see something going on in that 1700 range? Do I see any shark peaks here? No. So that means no C double bond O.
She just.
That's the way that I analyze it. Which means out. 50-50.
She's already doing this.
Yeah. Do I see the 3200 to 3500 shark peak? I do. Do you? It means alcohol. But A and D are both alcohols. How can I know which one it is? Is it A or is it D? Is there something else that can help me? Ramon.
The percentages of carbon, hydrogen, and oxygen.
And what can we do with that? Find the empirical formula.
Yay!
Yes, one of those basic ideas back from pre-ACE CAP that you can use percentages to find out your amount of carbons, hydrogens, and oxygens in your simplest version of the molecule. How do we do that again? Back to basics. Where would we begin? What do we do with that percentage? Do you remember?
The lowest one.
Okay, but is it just the lowest one, or do we have to do something to it first?
Divide.
What was step one? Chelsea. Divide by the molar masses, the MRs, right? So divide carbon by 12, hydrogen by 1, oxygen by 16. And that gives us we gotta solve it. 62.07 divided by 12.
32.07.
Ah, 5.17, 10.34, and this is like, I solved it earlier, but 1.72. Now what do we do with these numbers?
Yeah, the lowest one.
Now we divide by the smallest. Do you remember that step? So once we change the grams to moles, we divide by the smallest. So divide all these by 1.72. That makes this 1. That makes this 6. And that makes this 3. Okay. So C3, H6O1 is the empirical formula of our molecule. Neither of those molecules have 3 carbons. How many do they have? 1, 2, 3, 4, 5, 6, right? So multiply all this by 2. C6, H12O2. So which of these is C6, H12O2? A. How'd you do that so quick? How did you do it? Yeah, how did you know that that A was C6H12O2? That means take 2 hydrogens away. So this one actually, you can count them out. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This is 14 hydrogens. When you close the ring, you take away 2 hydrogens, right? So that's why this is 12 hydrogens. Is A? A is the answer.
Sweaty.
Welcome back. All right, let's try one more. Oh no, there's 2 more. So many practices. I did this earlier in class and doesn't want to do it. Okay, just to make sure you got it. What is this one? I always look for 2 peaks. I look for, and then I analyze further after that. So I'm looking for, do I see 1700? Yes. So we know that this is going to be a C double bond O thing. 5. Okay, do I see 3200 to 3500? The answer is no, you don't. right? So you don't have the alcohol bond. So what else is there that's important that looks like it could tell us some information? You've got something big going on over here that wasn't present in any of the other graphs, right? And you've also got something pretty strong over there. So what do those two pieces of information tell you that this could be? Go ahead.
C single bond O.
This tells me C single bond O is there. Wait, so C single bond O is there and C double bond O is there. So this functional group must be something like this. The question is, what comes after this? Is this an H or a C? Because that tells me if this is an ester or if this is a carboxylic acid. Let's take a look back at the chart. Esters are 1710 to 7250 and 1040 to 1300. What about carboxylic acid?
There's no OH.
No, but there's three different places for OH groups. Doesn't it say that here? If it's an alcohol, it's the 3200 to 3600. If it's a carboxylic acid, it's based between 2500 and 3000.
Oh, yeah, this thing.
Do you have a very broad 2500 to 3000?
Yeah.
Yes, this is a carboxylic acid. And so the correct answer here that they expected you to come up with is that this is a carboxylic acid. Because of this right here. This was the OH of the carboxylic acid. Right there. Okay, this is the last question for IR. Yes, the resonance. We're at least gonna introduce it. Can't leave the class without at least introducing it. Next class will be a big one though, because you're gonna have to go like run through most of NMR on Friday, so have your brains ready. All right, so the infrared spectrum of propanoic acid produced by reaction 2 is shown. Describe and explain the difference between W, which is whatever this is, and propanoic acid. So they're telling you, hey, this is propanoic acid. We are presenting you with the graph for propanoic acid. What's the difference between that and W? How do I find out what is W? Caesar?
No.
It's a reduction! What do carboxylic acids become? They become aldehydes, right? But aldehyde don't stay aldehyde. What does aldehyde then become? They become alcohols. The most reduced form of a carboxylic acid is an alcohol. Will these reactions be coming back in Unit 6? Yes, they will. Have your flashcards. This is just kind of a primer to get you ready for that. So W is,
Are you ready?
that's the final unit of study, right? Is organic. W is that.
That's right.
So now we can describe and explain the main difference. So what would be in this graph that isn't in W's graph? Isa, yes. There is a strong P around 1710 in propanoic acid that would disappear in W. So it's only 1 mark, so that's fine. Well, actually, there's 2 marks. The second is to say that would disappear in the other. But if you needed to say more than this, you could have also said that in W, there would have been a stronger peak at 3200 to 3400, and the 2500 to 3000 would go away. Because it's not a carboxylic acid, it's a regular alcohol. So that's the more you could have said if you needed to explain more. But this was enough for the marks. Okay, so for the end of the class today, I do have a video. I'm going to stop recording at this point, and we will do most of NMR next class and see how far we get into it. But I want to introduce the concept of it